Mathematics often feels like a collection of separate, intricate worlds. But what if two of its most distant realms are actually perfect reflections? Homological mirror symmetry is that profound bridge, a mathematical Rosetta Stone translating between the dynamic world of shapes in motion and the rigid world of algebraic equations. This is not just an abstract curiosity, it is a key that unlocks a deeper layer of reality itself. By the end of this journey, you will understand how this elegant symmetry could reshape future technology, from quantum computers to artificial intelligence. We will uncover how a conjecture from string theory became a computational superpower and ask why the universe seems to speak in dualities. What hidden connection between order and motion most captivates your imagination? That name, homological mirror symmetry, sounds like a daunting fortress of jargon, but every great fortress has a gate, and the key is simply understanding the words. Let us start with symmetry. We all recognize symmetry in a butterfly's wings or a snowflake, a perfect correspondence between two halves. Here, the symmetry is not visual but informational. It is a deep mathematical equivalence where two things are fundamentally the same in their structure, even if they look nothing alike. The mirror part tells us this is a duality, a reflection. Think of how your left and right hands are mirror images, similar yet opposite. In this theory, two mathematical universes are mirror reflections of each other. Now, homological. This is the most technical sounding piece, but its core idea is beautifully intuitive. In geometry, we want to do more than just look at shapes. We want to measure their essential features, like counting holes. A donut has one hole, a pretzel has three. Homology is a sophisticated, algebraic way of cataloging these features, a precise inventory system for the voids and tunnels within a shape. It is the mathematics of counting what is not there to understand what is. So, homological mirror symmetry, in plain language, is the astonishing proposal that two profoundly different kinds of geometric spaces can have identical inventories of essential features. They are informationally twins, even if they are built from entirely different materials. One space is called a symplectic manifold. This is the realm of physics and motion. Picture the phase space of a swinging pendulum, where every point captures both its position and its momentum. It is a geometry built for dynamics, for things that flow and change. The other space is a complex algebraic variety. This is the realm of pure, rigid equations, like the graceful curves defined by polynomial formulas. It is a geometry of perfect, frozen relationships. The conjecture of homological mirror symmetry boldly states that for a given symplectic manifold, there exists a mirror complex variety such that their homological categories, their master inventories, are mathematically identical. It is as if you have the same epic novel written in two alien languages. One language uses symbols of motion and energy, the other uses symbols of static, crystalline equations. To the untrained eye, the pages look completely different, alien scripts with no connection. But a master translator, using the rules of category theory, can demonstrate that every plot point, every character arc, every twist in the story of one is perfectly captured in the other. The story, the soul of the information, is one and the same. This is not a vague similarity, it is a precise dictionary-level equivalence. Why would the universe or mathematics bother with such an elaborate double description? The profound implication is that these two languages tell the same story. To understand the plot, we must meet the main characters. On one side of the mirror stands symplectic geometry. This is the mathematics of motion and energy. Picture the vast, abstract canvas where a physicist plots every possible state of a physical system. This is phase space. For a single planet orbiting a star, a point in this space captures both its exact position and its exact momentum at that instant. The entire, graceful ellipse of its orbit unfolds as a curve on this canvas. Symplectic geometry provides the rules for measuring areas on this canvas, not with a ruler, but by tracking how things flow and swirl within it. It is the natural language of Hamiltonian dynamics, describing everything from the rhythmic swing of a pendulum to the chaotic dance of celestial bodies. Think of a robotic arm moving through its range of motion, each possible configuration and velocity mapped to a point in a high-dimensional symplectic space. The geometry here is soft, fluid, and dynamic, built for tracking change. Now peer into the mirror's reflection. Here we find complex algebraic geometry, a world of breathtaking order and rigidity. This realm deals with shapes defined not by motion, but by pristine polynomial equations where the variables are complex numbers. These are numbers with two parts, a real and an imaginary component, granting an extra dimension of freedom. The solutions to these equations form shapes of stunning intricacy, like the Calabi-Yau manifold. Imagine a shape so exquisitely curved that at every point it looks like a complex number plane, a delicate, multi-dimensional latticework of pure relation. There is no flow here, no momentum. This is a frozen, crystalline landscape of perfect mathematical harmony. For generations, these two disciplines lived in separate wings of the mathematical palace. Symplectic geometers spoke the language of physics and dynamics. Complex algebraic geometers spoke the language of abstract form and equation. They used different tools, asked different questions, and saw the universe through entirely different lenses. Homological mirror symmetry makes a claim so bold it reshapes the palace floorplan. It declares that these are not separate wings at all, but two sides of the same coin. For a given symplectic space humming with dynamic possibility, there exists a mirror twin, a complex algebraic shape, whose rigid, equation-defined structure contains exactly the same encoded information. The swirling vector fields of planetary motion find a perfect, silent counterpart in the intricate lattice of a Calabi-Yau manifold. How can the language of orbits and the language of polynomials possibly be translated into one another? The bridge between these worlds is built not with equations but with relationships. To truly grasp the mirror, we need to understand the translator, a framework so universal it is called the programming language of modern mathematics, category theory. Forget thinking about mathematical objects as isolated islands. Category theory invites us to map the entire network of connections between them. A category consists of two simple ingredients. First, objects. In our story, an object could be a symplectic manifold, that dynamic phase space, or a complex algebraic variety, that frozen crystalline shape. Second, and most importantly, morphisms. These are the allowed transformations, the bridges you are permitted to build from one object to another. In geometry, a morphism might be a smooth, continuous deformation, like stretching a rubber sheet without tearing it. The power of this perspective is radical. Instead of obsessing over what a shape is made of, its raw points and coordinates, category theory asks, what can this shape do? How does it connect to everything else? By studying the category of a space, we extract its relational DNA, a complete blueprint of how it interacts with its mathematical universe. This is why two spaces that look utterly alien can be secretly twins. They can be built from completely different materials, yet possess identical networks of relationships. Their categorical blueprints match. This leads to the profound idea of an equivalence of categories. It is a perfect dictionary-style translation between two mathematical worlds. Every object in the symplectic category finds a unique counterpart in the complex algebraic category. More crucially, every possible relationship, every morphism between symplectic objects, has a precise mirror-image relationship between the corresponding algebraic objects. Nothing is lost in translation. The entire dynamic, flowing structure of one world is perfectly encoded in the static, relational lattice of the other. So when homological mirror symmetry states that the category of a symplectic manifold is equivalent to the category of its mirror complex variety, it is making a claim of breathtaking precision. It says the story of motion and the story of form are, at their deepest structural level, the same story written in two languages. The mirror is not a vague metaphor, it is a rigorous categorical isomorphism. What could such a perfect duality possibly be used for? This elegant idea did not emerge from pure mathematics alone. It was a gift from the frontier of theoretical physics, specifically from the quest for a theory of everything, string theory. In the mid-1990s, physicists like Andrew Strominger, Xing-Tung Yao, and Eric Zaslow were wrestling with a profound question. If our universe has tiny, curled-up extra dimensions as string theory suggests, what shape do they take? The leading candidates were Calabi-Yau manifolds, those intricate, multi-dimensional shapes from complex geometry. In their calculations, something bizarre and beautiful kept happening. For a given Calabi-Yau manifold that solved their equations, they often found what they called a mirror partner, a different Calabi-Yau where certain mathematical properties seemed to swap places. It was as if the universe's instruction manual had two perfectly valid editions, written in complementary languages. The physicist's insight, known as the SYZ conjecture, proposed a geometric recipe for constructing this mirror by essentially trading complex structure for symplectic structure. This was a physicist's intuition, a powerful hint from the cosmos, but it took a mathematician to hear that hint and build a cathedral from it. In 1994, Maxim Kontsevich attended a string theory conference. He listened to the physicists describe their mirror pairs and their swapping of roles, and he had a revelation. He realized this physical duality could be captured with breathtaking precision using the language of category theory. In a now legendary lecture, Kontsevich proposed the homological mirror symmetry conjecture. He stated formally that the category of Lagrangian submanifolds, which are key objects in the symplectic world of a Calabi-Yau, is equivalent to the derived category of coherent sheaves, the corresponding algebraic objects on its mirror partner. This was the moment of crystallization. The physicist's observation of a strange partnership became a mathematician's rigorous blueprint for a perfect translation. Kontsevich's conjecture did not just bridge two kinds of geometry, it built a superhighway between two entire cultures of thought. It gave mathematicians a powerful new dictionary, allowing them to take a problem that was impossibly hard in one world, translate it across the mirror, solve it in the other world where the tools were better, and then translate the answer back. A dynamical puzzle about flows and cycles could become an algebraic puzzle about sheaves and sequences, suddenly tractable. This was the ultimate interdisciplinary handshake, where the speculative dreams of physics provided a map to hidden continents of pure mathematics. The conjecture became a beacon guiding a generation of explorers. Kontsevich's blueprint gave us the map, but to cross the bridge we must first understand the landscape on this side. In the dynamic, flowing world of symplectic geometry, the central characters are not just any shapes but special ones called Lagrangian submanifolds. Think of a calm, flat membrane suspended within a swirling, energetic fluid. This membrane has a magical property. It perfectly captures the state of minimal action, a cornerstone principle of physics. In the phase space of a pendulum, a Lagrangian could represent the set of all points where it is momentarily at its highest position, zero momentum, ready to fall. It is a snapshot of potential. These Lagrangians are the fundamental objects in the first great category of the mirror, the Fukaya category. Named after the mathematician Kenji Fukaya, this category is the master inventory of all possible Lagrangian submanifolds within a symplectic space. But a list of objects is meaningless without understanding how they interact. This is where the Fukaya category reveals its genius and its deep connection to physics. The morphisms, the fundamental relationships between two Lagrangian objects, are defined by their intersections. Picture two of those calm membranes floating in our symplectic fluid. Where they cross, you get a point. In the Fukaya category, each intersection point is not just a location, It is a potential event, a possible trajectory for a dynamic process. The real magic is in the counting. We do not just tally intersections like beans in a jar. We use an advanced tool called flow homology, which counts not the points themselves, but the special surfaces that connect them. Imagine a ghostly film stretching between two intersection points, like a soap bubble film minimizing its area. Flow homology counts these films, these trajectories, in a way that respects the symplectic flow. This makes the Fukaya category inherently computational and physical. It is built from the language of paths, of histories, of things happening. It asks dynamical questions. If I start here at this intersection, what are all the possible ways, all the minimal energy paths I could take to get to that other intersection? The entire structure feels soft and probabilistic, dealing with counts of possibilities rather than fixed, rigid equations. It is the mathematics of process and connection written in the dialect of motion. This is the symplectic side of the mirror, a world catalogued not by what is statically there, but by what can dynamically occur between its parts. Across the mirror, in the realm of the complex algebraic variety, the language shifts from motion to meticulous order. Here, the fundamental objects are not membranes in a fluid, but structures called coherent sheaves. A sheaf is a brilliant organizational device. Imagine taking a complex geometric shape, like that intricate Calabi-Yau manifold, and covering it with a patchwork of overlapping neighborhoods. On each open patch, you attach a specific piece of algebraic data, like the set of all well-behaved complex-valued functions defined just on that patch. A sheaf is the rulebook that consistently glues all this local data together across the overlaps. It is a global filing system for algebraic information, where every function on a small region knows how to connect with its neighbors on the border. A coherent sheaf is a particularly nice, well-behaved version of this system, one that allows for more sophisticated data than just functions, like vector spaces or modules, to be attached to each patch. The derived category of coherent sheaves is the grand, organized library built from these filing systems, but it is not just a catalog of individual sheaves. The real power and the reason for the word derived comes from working with complexes of sheaves. Think of a complex as a carefully arranged sequence of sheaves connected by special maps, like a chain where each link transforms information into the next. This structure allows mathematicians to capture extremely subtle algebraic relationships, resolutions of singularities, and hidden symmetries that a single sheaf could never reveal on its own. The derived category is the universe where these entire chains are treated as fundamental objects. In this library, two different chains that ultimately convey the same algebraic story are considered equivalent. It is a world obsessed with the essence of information, not its raw packaging. This contrasts starkly with the Fukaya category's world of possibilities. Where Fukaya counts ghostly films between intersection points, the derived category manipulates exact sequences of algebraic functions. One side deals in trajectories and probabilities, a geometry of what could happen. The other side deals in precise constraints and equations, a geometry of what must be true. The mirror symmetry conjecture asserts that these two magnificent, sprawling libraries, built from entirely different materials and governed by completely different rules, are nonetheless perfect translations of each other. Every Lagrangian brain and its web of flow trajectories in the symplectic world finds a precise counterpart in some complex of coherent sheaves and its algebraic maps in the mirror world. The dynamic story of connection is faithfully recorded as a static story of relation. This equivalence turns impossible problems into solvable ones. A question about counting certain paths in a chaotic symplectic space might be an intractable mess of analysis, but its mirror translation could become a straightforward exercise in linear algebra within the derived category. The mirror is not just a philosophical curiosity, it is a computational engine. The true power of this mirror lies not in its existence but in its operation. A perfect dictionary must provide explicit rules for translation, and in homological mirror symmetry, that dictionary is called the mirror functor. A functor is the workhorse of category theory, a machine that takes every object and every relationship from one category and systematically converts it into its counterpart in the other. It is the precise algorithm of the mirror, the step-by-step procedure that turns a question about motion into a question about algebra. Consider a single Lagrangian brane, that calm membrane in the symplectic sea. To the mirror functor, this is not just a shape, it is an input. The functor processes this input, performing a series of profound mathematical operations, and out puts an object on the algebraic side, a specific complex of coherent sheaves. The brane's position, its topology, all its dynamic potential get encoded into a particular sequence of algebraic modules and maps. This is already astonishing, but the functor's real genius is with relationships. Remember those intersection points between two Lagrangians, which the Fukaya category interprets as possible events. The mirror functor takes each of these intersection points and translates it into a specific algebraic map between the two corresponding complexes of sheaves. The physical possibility of moving from one state to another becomes a rigid algebraic instruction for transforming one piece of data into another. Even more remarkably, the ghostly flower trajectories, the soap films that connect intersections, get translated into the intricate compositions of these algebraic maps. The entire probabilistic, flowing structure of possible histories is captured perfectly by the exact, deterministic logic of algebraic sequences. Constructing this functor for a given pair of mirror spaces is the central Herculean challenge of the field. It is not enough to know the two libraries are equivalent. Mathematicians must write the exact translation manual between them. In celebrated examples, like for the basic two-dimensional torus, this has been achieved. The result feels nothing short of miraculous. A Lagrangian circle on a symplectic torus might correspond to a sheaf that is essentially a line bundle, a twist of algebraic data over the mirror elliptic curve. The intersection count of two circles, a simple geometric fact, manifests on the other side as the dimension of a space of algebraic sections, a completely different kind of calculation. The translation is never obvious. It is a deep, often shocking revelation. It is as if you handed a translator a poem about the feeling of wind, written in a language of gestures and sighs, and they returned with a sonnet about the structure of a leaf, written in a language of crystalline lattices, yet every emotional nuance of the original was preserved. This functorial mirror map is the engine that transforms a beautiful conjecture into a practical tool. It allows a mathematician to take a dynamical system, encode it as a configuration of Lagrangian branes, send it through the mirror functor, and receive back an algebraic problem that might be orders of magnitude easier to solve. The answer, when translated back, reveals truths about the original system that were completely hidden from view. The mirror is not a passive reflection, it is an active computational portal. The simplest gateway to this computational portal is a humble donut. This shape, a two-dimensional torus, is known in mathematics as an elliptic curve. It is the most basic stage where homological mirror symmetry performs its magic in full, checkable detail. Imagine a square sheet of rubber. Now glue the top edge to the bottom edge to form a cylinder. Then glue the left edge of that cylinder to its right edge. You have created a torus, a surface with one hole, a geometric playground with both symplectic and complex personalities. On this torus, we can paint a symplectic structure, a way to measure areas that makes it a dynamic phase space. We can also paint a complex structure, a rigid lattice of coordinates that makes it an algebraic curve. The complex structure is controlled by a single, crucial number called tau. Picture tau as a twist parameter. It dictates how the square is skewed before we glue it, defining the angles and proportions of the lattice on the donut surface. Now here is the first glimpse of the mirror. For an elliptic curve with complex structure tau, its mirror partner is another elliptic curve with complex structure -1 divided by tau. This simple fractional transformation is the seed of the entire duality. It swaps the roles of the symplectic and complex data in a precise algebraic dance. Let us populate the symplectic side. In the Fukaya category of this torus, our objects are Lagrangian submanifolds. On a two-dimensional torus, these are simply closed, non-contractible circles, like loops of string wrapped around the donut's hole or around its body. A given circle is defined by its slope, how many times it winds around each fundamental direction. A circle with slope 0 might go purely around the equator. A circle with an infinite slope might go purely around the meridian. Each possible slope gives us a distinct Lagrangian brane, a distinct object in our category. The morphisms between two such circles, their intersections, are just the points where they cross on the torus's surface. The Floer homology counts the trajectories between these points, which in this simple case relates directly to the angles between the circles. It is a clean geometric inventory. Now cross the mirror to the algebraic side. Here, our elliptic curve is defined by that complex parameter tau. The objects in the derived category are complexes of coherent sheaves. In this basic setting, the most important sheaves are line bundles. Think of a line bundle as a consistent way of attaching a complex number line, like a tiny ruler, to every point on the curve, but with a prescribed twist. The amount of twist is measured by an integer, the degree. A line bundle of degree 0 is trivial, like attaching the same ruler everywhere. A line bundle of degree 1 gives a full 360-degree twist as you go around the curve. This integer degree is the algebraic counterpart to the geometric winding number of a circle. The mirror functor provides the exact translation manual. It declares that a Lagrangian circle on the symplectic torus, with a specific slope determined by the symplectic area it encloses, corresponds precisely to a specific line bundle on the mirror algebraic curve with a degree determined by that same data. For instance, a simple circle wrapping the meridian of the symplectic torus might be sent by the functor to the line bundle of degree 1 on the mirror curve. The miraculous check is in the morphisms. The number of intersection points between two Lagrangian circles, a geometric count, must equal the dimension of the space of algebraic maps between the two corresponding line bundles, an algebraic calculation. And they do. This equivalence is not a vague analogy, it is a theorem. We can compute on both sides and get identical answers. This transforms the abstract, dizzying conjecture into something you can, in principle, test with pencil and paper for this simple case. The elliptic curve is our Rosetta Stone, proving the two scripts describe the same reality. If the mirror works for the donut, could it illuminate the vast, hidden geometries of our own universe? The donut reveals the mirror's logic, but the real universe is woven from far richer fabric. To see its true power, we must ascend into higher dimensions, to the geometric objects that string theory suggests might shape reality itself, Calabi-Yau manifolds. Among these, one stands as a legendary testing ground, the quintic threefold. Imagine a universe defined by a single, deceptively simple equation in five-dimensional complex space. The equation is this: x to the fifth power plus y to the fifth plus z to the fifth plus w to the fifth plus v to the fifth equals 0. This is the quintic threefold. It is a three-complex dimensional shape, which means from our human perspective it has 6 real dimensions, an intricate, folded labyrinth of breathtaking complexity. It is a specific and immensely important example of a Calabi-Yau manifold, possessing the precise kind of curvature that makes it a candidate for the hidden, curled-up dimensions of our cosmos. For years, mathematicians struggled with a fundamental question about this shape: how many distinct rational curves does it contain? A rational curve is like a perfect, one-dimensional sphere, a bubble of geometry, embedded within the vast 6-dimensional labyrinth. Think of it as finding all the possible, perfectly round loops of string that can be laid on this hyperdimensional surface without breaking. Counting them is not straightforward because curves can exist in different degrees, like simple circles or more complex twisted paths. The number of degree 1 curves, the simplest ones, is famously 287,500, but the number for degree 2 curves. That was a monumental puzzle. Computing these numbers directly, called Gromov-Witten invariants, is a Herculean task in symplectic geometry, involving the mind-bending analysis of all possible pseudo-holomorphic curves, essentially all the ways a two-dimensional sheet can map into this space. It is a dynamic, messy problem of counting possibilities in a flowing landscape. Then, the mirror offered a breathtaking shortcut. Physicists Brian Greene and Ronan Plesser, building on the SYZ framework, showed how to construct the mirror partner of this quintic threefold. They did not create a new shape from scratch, but revealed it through a process of orbifolding, a kind of sophisticated folding and identifying of symmetries within the original. The mirror quintic is a different Calabi-Yau, intimately related yet algebraically distinct. Homological mirror symmetry asserts the Fukaya category of the original quintic, with all its dynamical curve counting data, is equivalent to the derived category of coherent sheaves on the mirror quintic. This is where the magic becomes practical. The impossibly difficult problem of counting rational curves on the original symplectic manifold translates across the mirror functor into a vastly more manageable problem on the algebraic side. On the mirror quintic, the question becomes one of computing periods and solving a system of differential equations known as the Picard-Fuchs equations. This is a problem of classical analysis and algebra, difficult in its own right but equipped with centuries of developed tools. Mathematicians like Philip Candelas, Xenia de la Ossa, Paul Green, and Linda Parks performed this translation. They took the algebraic data from the mirror, performed their calculations, and read off the numbers, the curve counts for the original quintic. The results were stunning and definitive. They computed the number of rational curves of every degree up to 10, numbers that were previously completely unknown and seemingly unreachable by direct methods. The mirror did not just suggest an answer, it provided a full, verifiable catalog. This was the moment the conjecture moved from beautiful theory to undeniable computational superpower. A problem born from the dynamics of shapes in motion was solved in the silent, crystalline language of equations. The mirror is not merely a philosophical duality, it is the ultimate problem-solving engine, turning the opaque into the calculable. What other impossible questions might this engine crack open? Perhaps even questions about the fabric of our own physical world. This computational shortcut is nothing short of a revolution in enumerative geometry, the art of counting geometric objects meeting specific conditions. For centuries, mathematicians dreamed of answering questions like, how many lines pass through 4 given points in space? But as the spaces grew more exotic, like our quintic threefold, direct counting became a logistical nightmare of infinite possibilities. Homological mirror symmetry provided the ultimate hack. Instead of brute forcing the count in the chaotic symplectic arena, you simply consult the mirror. The entire messy problem of counting pseudo-holomorphic curves, those ghostly sheets mapping into the space, translates across the duality into a clean, classical problem on the algebraic side. There, the enigmatic curve counts re-emerge as the coefficients of a power series solution to a well-studied system of differential equations, the Picard-Fuchs equations. It is as if you needed to count every single grain of sand on a vast, stormy beach by hand, a nearly impossible task. But the mirror hands you a sealed box from the beach's twin on another planet, and inside that box is a single, elegant barometer. By reading the pressure on that gauge, you can deduce the exact sand count back on the original shore. The algebraic machinery does the counting for you. You start with an intimidating period integral, an expression that sums up the complex geometry of the mirror manifold. manipulating this integral leads directly to the Picard-Fuchs equations. Solving these equations yields a power series, and hidden within the coefficients of that series, like a secret code, are the precise numbers of curves of each degree. The number 287,500 for lines on the quintic is not found by drawing them. It is extracted from the solution of a differential equation that emerged from the mirror. This perspective transformed the field. Problems that would have consumed a lifetime or remained forever out of reach became tractable with the mirror map. It granted mathematicians a computational superpower, allowing them to bypass the intractable dynamics and mine answers from the orderly realm of algebra. The mirror is not just a bridge between worlds, it is a teleporter, sending you instantly to the version of the problem where the tools are sharpest and the path is clear. If a simple differential equation can count the hidden curves of a six-dimensional universe, what other profound secrets might this duality unlock when applied to the algorithms of tomorrow? The curve counts on the quintic are a spectacular demonstration, but the mirror's power originates in a deeper, more fundamental layer of reality. This is the layer where mathematics and quantum physics become indistinguishable. To understand that, we must meet the two faces of topological string theory. In physics, string theory proposes that the fundamental constituents of the universe are not point particles, but tiny, vibrating loops of energy. Topological string theory is a simplified yet profoundly rich version that freezes ordinary motion to focus purely on the shape of the world sheet, the surface traced out by a string as it moves through spacetime. This theory splits into two complementary perspectives, known as the A model and the B model. The A model is blind to the detailed metric of space, caring only about its symplectic structure, the geometry of areas and phases. It counts how strings can wrap around cycles in space, a process deeply tied to the dynamics of instantons and quantum tunneling. The B model, by contrast, is sensitive only to the complex structure of space, the rigid, algebraic lattice of coordinates. It probes how strings interact with the background geometry through holomorphic quantities, things that depend smoothly on the complex coordinates. For years, these were seen as two separate, self-consistent theories of the topological string. Then came the physicist's revelation: they are mirror duals. The A model on one Calabi-Yau manifold is physically equivalent to the B model on its mirror partner. This is not a mathematical curiosity, it is a statement about the unity of physical law. The same quantum physics can be described in two radically different geometric languages. Homological mirror symmetry is the precise mathematical crystallization of this physical duality. The Fukaya category, with its Lagrangian branes and Floer trajectories, provides the complete mathematical formalism for the A model. Each Lagrangian brane represents a possible boundary condition for an open string, a D brane. The morphisms in the category, those intersection points and connecting trajectories, encode the spectrum of strings stretching between different D branes. It is a complete catalogue of possible interactions in the symplectic description of the world. On the other side of the mirror, the derived category of coherent sheaves provides the complete mathematical formalism for the B model. The sheaves represent the D branes in the complex picture, and the algebraic maps between them encode the open string spectrum in that language. When Kontsevich formulated his conjecture, he was essentially providing the rigorous mathematical backbone for the physicist's mirror symmetry of topological strings. This turns abstract categories into a laboratory for fundamental physics. Concepts that are elusive in the full, 10-dimensional fury of superstring theory become tractable and well-defined in this topological realm. For instance, the charge of a D brane, a fundamental property in string theory, finds a natural home in these categories. In the derived category of sheaves, the charge is identified with the Chern character, an algebraic invariant that sums up the twisting data of the sheaf. In the Fukaya category, the charge corresponds to the homology class of the Lagrangian, a topological label for the brane's shape. The mirror functor ensures these two notions of charge are perfectly matched across the duality. So a physicist wondering about the spectrum of strings between a specific set of D branes in a complex geometry can, via the mirror, translate that question into a problem of counting intersections of Lagrangians in a symplectic geometry, and vice versa. This is the ultimate payoff. Pure mathematics, developed for its own sublime beauty, provides the exact language and tools to model the hypothesized objects and interactions of our universe at its most fundamental scale. The categories are not just analogous to the physics, they are the physics written in the dialect of absolute abstraction. If our cosmos is indeed built upon such mirrored geometric foundations, what does that say about the nature of reality itself? These abstract categories are more than just a language for physics. They could be the blueprint for the next leap in computation. The deep architecture of homological mirror symmetry, with its perfect networks of relationships, holds startling implications for the future of quantum information. At its heart, a category is a map of possible transformations. Every object is a state, and every morphism is an allowed operation to move from one state to another. Now picture a quantum computer. Its fundamental unit is the qubit, a particle that can be in a superposition of states, 0 and 1 at once. A quantum algorithm is a precisely choreographed sequence of quantum gates, each gate a tiny operation that manipulates the fragile quantum state of those qubits. This sequence from initial input to final output is a quantum circuit. Look at the structure of a category and you will see a profound similarity. The objects are like the possible quantum states of a system. The morphisms, the arrows connecting them, are precisely the allowed quantum gates. Composing morphisms, chaining one arrow after another, is identical to building a quantum circuit from individual gates. The entire categorical framework is a mathematical universe built for describing processes, transformations, and information flow, which is exactly what quantum computation is. But HMS offers something far richer than a simple analogy. It provides two perfect dual descriptions of the same informational reality. In one universe, information is encoded in the soft, dynamic geometry of Lagrangian branes and their intersections, a world of paths and possibilities. In the mirror universe, that same information is frozen into the rigid, algebraic structure of sheaves and their maps, a world of exact constraints and equations. This duality suggests a radical idea for quantum hardware. What if we could build a quantum computer that embodies this mirrored structure, one where a quantum state is not just a collection of qubits, but is represented by a configuration in a symplectic geometric space, like a specific arrangement of Lagrangian membranes? A quantum operation would then be a physical process that evolves this geometric configuration, perhaps by moving these membranes through each other in a controlled way. The beauty is that due to the mirror, this entire messy physical process would have a perfect algebraic counterpart. Every geometric move would correspond to a precise, error-checkable algebraic transformation on the mirror side. This could lead to fundamentally new kinds of error correction. In our current quantum computers, decoherence, the leakage of quantum information into the environment, is the greatest enemy. We fight it with complex codes that redundantly encode information across many physical qubits. But what if the information was encoded not in fragile individual particles, but in the global topological properties of a geometric system, like the winding numbers of a Lagrangian brane or the Chern class of a sheaf? These are properties that cannot be disturbed by small, local nudges, only by large, catastrophic changes. This is the promise of topological quantum computing, and the language of HMS is its native tongue. The stability comes from the fact that the information is stored in the shape of the world itself, not in its volatile details. A quantum gate in such a system might be performed by braiding these topological objects around each other, a process where the exact path does not matter, only the overall topology of the braid. This is directly analogous to how the Fukaya category cares about the overall count of trajectories between intersections, not their precise classical paths. The mirror duality then provides a powerful check. Any computation performed by braiding Lagrangians in the symplectic world must yield an answer that is perfectly mirrored by a sequence of algebraic manipulations on sheaves. If the two answers disagree, you have detected an error not in the software, but in the very fabric of your computational space. This transforms the mirror from a mathematical curiosity into a potential hardware-level protocol for fault tolerance. We are not just simulating a category, we are asking the universe to compute with it, using the deep geometric principles of duality and equivalence that may already underpin reality. Could the secret to a stable quantum future be written in the language of sheaves and Lagrangians? The stability of a topological quantum computer relies on the shape of information itself. But this same geometric language may soon reshape the intelligence that designs our world. The principles of homological mirror symmetry, this dance between dynamic form and rigid equation, are beginning to whisper to the field of artificial intelligence, particularly in the quest to generate and understand optimal shapes. This is algorithmic geometry, where AI does not just analyze data, but learns the deep grammar of space. Consider a future design lab. An engineer needs a new catalyst with a microscopic structure that maximizes surface area for chemical reactions, or an architect seeks a roof form that is both stunningly beautiful and perfectly load-bearing. Today, we might simulate countless random iterations, a brute force search through a universe of possible forms. But what if the AI had an innate sense of geometric duality? Imagine training a deep learning model not on images of shapes, but on the categorical blueprints of thousands of verified mirror pairs. The AI's training data would be the Fukaya categories of symplectic manifolds and the derived categories of their complex algebraic mirrors. It would learn the hidden correspondence, the mathematical DNA that links a flowing, energetic geometry to its crystalline, equation-based twin. Once trained, such a system could perform a staggering feat. Presented with a brand new, hyper-complex shape from a materials science simulation, perhaps one defined by symplectic data about stress and flow, the AI could predict its mirror partner. It would not calculate it through years of laborious mathematics, but infer it almost intuitively based on the patterns it learned from the categorical dictionary. This predicted mirror would be a gift. Suddenly, the intractable dynamical properties of the original material, its response to forces and vibrations, could be studied through the lens of the mirror's algebraic geometry, where stability and rigidity might be far easier to analyze. You could ask the AI, what is the mirror of this proposed bridge truss geometry? And the algebraic shape it generates might reveal hidden resonant frequencies or stress points invisible in the original model. This is not science fiction. The core mechanism here mirrors, quite literally, a breakthrough we already see in modern AI. Think of a neural network that translates English to French, or one that generates a textual description from a photograph. These systems learn a deep functional map between two very different domains, language and vision. They build an internal model of equivalence, a learned functor. The image of a cat is not stored as pixels, but is associated with a pattern of activation that also corresponds to the word sequence, a small furry feline. This is precisely what the mirror functor does. It is nature's own perfect, pre-existing translation network between the domain of symplectic data and the domain of complex algebraic data. The categorical framework of HMS could therefore inspire entirely new machine learning architectures. Instead of layers of simple neurons, a network might be designed with layers that explicitly enforce categorical rules like compositionality and associativity, ensuring that the transformations it learns are not just statistical correlations but structurally sound maps. This could lead to AI that reasons with geometric objects directly, understanding that deforming a shape in a certain way must, by mathematical necessity, induce a specific change in its mirror representation. The AI's internal logic would be guided by the rigorous principles of equivalence, making its predictions more interpretable and fundamentally consistent. We are glimpsing a future where the deepest symmetries of mathematics become the guiding intuition for creative machines, where an AI designer, conversant in the language of sheaves and Lagrangians, dreams up forms for tomorrow's cities and technologies, forms that are born from a perfect balance of motion and form, a dialogue across the mirror. This speculative leap from AI to the cosmos might feel immense, but the mirror's logic compels it. If a single duality can connect geometry to geometry and geometry to physics, could it be the prototype for a universal language? Some of the most daring minds in physics and mathematics are asking precisely that. They suspect the true laws of the cosmos are not written in equations but in categories. Homological mirror symmetry stands as a stunningly successful case study, a proof of concept that categorical duality is not just useful but fundamental. It demonstrates that two seemingly independent descriptions of a system can be perfect reflections, linked by a precise functorial dictionary. This template of duality echoes in the most profound corners of theoretical physics. Consider the gauge-gravity duality, also known as the AD-SCFT correspondence. This is a conjecture that a theory of gravity in a certain warped spacetime, called anti-de Sitter space, is completely equivalent to a quantum field theory without gravity living on its lower dimensional boundary. It is a holographic principle where the information of a volume is encoded on its surface. On one side, you have the bending of spacetime and black holes, the domain of general relativity. On the other side, you have the swirling quantum chaos of particles and forces, like the strong nuclear force. They appear utterly different, yet the duality claims they are two languages for the same reality. Does this structure sound familiar? It is a mirror symmetry on a cosmic scale. The gravitational description, with its dynamical geometry, parallels the symplectic, a model side of HMS. The quantum field theory description, with its rigid algebraic structure of operators and correlations, parallels the complex B-model side. While the mathematical details are vastly more intricate, the philosophical blueprint is identical. Find the categorical framework that captures each world, then construct the equivalence of categories that serves as the translation manual. This is where ambitions like the Langlands program enter, a vast web of conjectures in number theory and geometry that also exhibits stunning dualities. Many see category theory as the grand loom on which all these patterns, from number theory to quantum gravity, are finally woven together. The goal is a unified categorical framework for reality, a single mathematical architecture that can manifest as geometry, as particle physics, or as number theory, depending on which functorial perspective you take. In this vision, homological mirror symmetry is not an endpoint but a guiding star. It shows us how to do the work of unification in a precise, computable way. The philosophical implications are dizzying. It suggests that what we perceive as fundamental forces or separate physical theories might merely be different choices of coordinate system in a vast categorical landscape. The universe is not described by a single set of equations, but by the network of equivalences between all possible valid descriptions. Our reality is the invariant, the story that remains true no matter which side of the mirror you read it from. This transforms our search for a theory of everything from a hunt for the ultimate equation to a mapping of the ultimate web of relationships. Could the final, elegant truth be that the cosmos is, at its heart, a perfectly self-consistent category? The universe rarely offers perfect, smooth shapes. Real geometry is filled with edges, corners, and boundaries. To bring the mirror's power into our world, mathematicians are now venturing into these rugged landscapes, extending homological mirror symmetry to spaces with singularities. Imagine a cone's sharp point or the crease where two surfaces meet. These are not flaws but features, and they are everywhere in applied geometry, from the stress points in a bridge to the crystalline defects in a semiconductor. Classical HMS, for all its beauty, dealt with pristine, closed Calabi-Yau manifolds. The new frontier asks what happens when we introduce a boundary or when we allow the space to develop a controlled singularity. The answer is leading to powerful generalizations like log HMS and the study of Landau-Ginzburg models. A Landau-Ginzburg model is in essence a geometric space paired with a potential function, a mathematical landscape with hills and valleys. This function introduces a directed flow, breaking the perfect symmetry of the closed Calabi-Yau and creating a kind of landscape with a destination. The mirror of such a model is not another smooth space, but a different kind of singular geometry. This expansion is crucial because it captures the mathematics of decay, of gradient flow, of systems that want to settle into a minimum energy state, which is the language of engineering and material science. To navigate these new mirrored pairs, mathematicians have enlisted a surprising visual ally, tropical geometry. Picture a mathematical amoeba. If you take a complex algebraic curve and plot its points using only the logarithms of their absolute coordinates, the intricate tendril-like shape collapses into a web of straight lines and vertices, a skeletal shadow. This shadow is a tropical curve. Tropical geometry translates the continuous, fluid world of complex numbers into a discrete, combinatorial world of piecewise linear graphs. It turns the subtle dance of holomorphic curves into a problem of counting integer-length segments and balancing conditions at vertices. This is a radical simplification. The mirror correspondence in this tropical limit becomes almost visual. The complex algebraic data on one side transmutes into a combinatorial arrangement of lines and weights on the other, which corresponds directly to the symplectic data of the mirror. You can literally draw the mirror. For a Landau-Ginzburg model, its tropical amoeba provides a polyhedral decomposition, a tiling of space that directly encodes the singularities and the potential function. The dual of this tiling, a new combinatorial skeleton, gives a blueprint for the mirror geometry. This makes the abstract functorial equivalence startlingly concrete. It is as if the deepest secrets of a quantum system could be faithfully represented by a child's construction kit of sticks and connectors. This combinatorial accessibility is a game changer for applications. An engineer modeling stress concentration at a sharp corner in a material could, in principle, represent that singularity as part of a Landau-Ginzburg model. The tropical picture of its mirror would then offer a discrete computational framework to analyze the flow of energy away from that stress point, translating a continuous problem in elasticity into a combinatorial optimization on a graph. The mirror is no longer confined to the rarefied air of theoretical physics and pure mathematics. It is growing roots in the soil of applied science. By embracing singularities and boundaries, mathematicians are not weakening the theory. They are arming it for the real world where perfection is an ideal, but edges are where the action happens. What new designs might emerge when our most advanced simulations speak this dual language of amoebas and skeletons? Behind every equation lies a human story of obsession and collaboration. The journey to map the mirror has been a global, generational effort, a testament to the collective imagination of mathematics. Maxim Kontsevich's initial conjecture was not a conclusion but a starting pistol. It ignited a quest that would draw in some of the world's most brilliant minds, each bringing their unique vision to bear on the problem. Dmitry Orlov, for instance, made profound contributions to understanding the derived category side, providing the rigorous algebraic framework needed to anchor the correspondence. Meanwhile, Paul Seidel's work on the symplectic side, particularly in flower theory and the Fukaya category, gave mathematicians the tools to navigate the dynamic world with unprecedented precision. These were not solitary geniuses working in isolation, but nodes in a vast, interconnected network of ideas, constantly building upon and challenging each other's work. The atmosphere was one of intense, joyful collaboration, where a breakthrough in Tokyo could instantly reshape a problem being tackled in Paris or Berkeley. This human network became the living embodiment of the categorical structures they studied, a web of relationships translating intuition into proof. One of the great collective triumphs was the eventual proof of homological mirror symmetry for projective spaces and toric varieties. These are the geometric arenas where the duality becomes particularly concrete, almost tangible, proving it required a staggering synthesis of tools. Deep geometric intuition guided the construction of the mirror functor, suggesting what the translation manual should look like, but then came the brute force computational verification, checking that the dictionary worked for an infinite family of objects and morphisms, a task demanding both algorithmic ingenuity and raw processing power. It was a marathon of creativity where moments of sudden insight would illuminate a path forward, only for the team to then spend months or years paving that path with unassailable logic. The process itself mirrored the duality it sought to prove, alternating between the fluid intuition of the symplectic world and the rigid, step-by-step algebra of the complex world. Stories from conferences and workshops paint a picture of a field alive with passionate debate. Whiteboards would fill with diagrams of amoebas next to lists of sheaves. Arguments over a single intersection count could last for days, and the shared language of categories allowed experts from disparate subfields to finally understand each other. This is the intellectual lifestyle at its most vibrant, a culture where the pursuit of abstract beauty is a communal, almost physical endeavor. The drive comes not from a desire for utility, but from a shared conviction that the mirror must be true, that such a perfect idea deserves a complete and rigorous foundation. Every proof cemented is a new territory mapped in this mirrored landscape, a victory for the entire community. Their work transforms the mirror from a speculative conjecture into a dependable tool, a bridge we can all now walk across. What new explorers will this bridge carry into the future, and what undiscovered continents might they report back from? Such abstract landscapes demand a new way of seeing. To truly grasp the mirror, we must learn to visualize its invisible architecture, using tools that turn algebraic whispers into geometric shouts. The challenge is profound. How do you depict a relationship between categories or show a duality that exists in 10 dimensions? The answer lies in a breathtaking fusion of art, computation, and imagination. Consider an animation of a Lagrangian torus, a donut shape, gently deforming within a symplectic space. As it twists and stretches, its intersection points with other Lagrangians bloom and vanish, a dynamic dance that visually represents the morphisms in the Fukaya category. This is not just a pretty picture, it is a moving diagram of possibility, showing how relationships are born from motion. Then shift your gaze to the other side of the mirror. Software can generate stunning, intricate renderings of Calabi-Yau manifolds, those 6-dimensional shapes from string theory. While we can only see a 3-dimensional shadow or cross-section, these visualizations, with their delicate folds and complex holes, make the alien beauty of the mirror's algebraic realm feel tangible. We see the crystalline structure that holds the frozen counterpart to all that symplectic flow. To bridge these worlds, we use network diagrams that map categories themselves. Picture a vast, intricate web where each node is a mathematical object, a brain or a sheaf, and each connecting line is a morphism, a possible transformation. These diagrams are the blueprints of the mirror functor, showing how every node in the symplectic web finds a partner in the algebraic web, and how every path between nodes has a mirrored path. It is a map of informational equivalence, a schematic for the universe's dual descriptions. Perhaps most surprisingly accessible are tropical amoeba plots. Remember, these are the skeletal shadows of complex curves. On a screen, you can watch as a lush, tendrilled algebraic curve, when put through a logarithmic transformation, collapses instantly into a clean, combinatorial skeleton of straight lines meeting at balanced vertices. This visual transformation is the mirror in action, making the deep correspondence between continuous geometry and discrete combinatorics something you can witness with your own eyes. Creating these visions is not magic, it is computational mathematics. Researchers and educators rely on powerful open-source platforms like Sage Math and specialized software like Mathematica to perform the heavy lifting. They input the equations of a Calabi-Yau or the data of a symplectic form, and the software computes the period integrals, solves the Picard-Fuchs equations, and even generates the first visual approximations of the mirror partner. These programs are the workshops where the mirror map is forged, turning conjectures into calculable, visualizable reality. But this toolkit is for more than just researchers in ivory towers. It is for communication, for teaching, for opening a window onto a world that was once sealed behind walls of impenetrable notation. When a student can manipulate a 3D model of a Calabi-Yau, rotate it, and see its holes, the concept of homology moves from abstract definition to intuitive understanding. When they can run a simulation that shows a Lagrangian intersection count change in real time as they adjust a parameter, they are not just learning, they are experimenting with the fabric of the theory itself. This is democratizing the beauty of deep mathematics. We are moving toward a future where advanced mathematical literacy is not just about symbolic manipulation, but about visual and intuitive fluency. The story of homological mirror symmetry, told through these dynamic visualizations, becomes a gateway. It invites everyone to appreciate that the most profound truths of our universe may not be written only in equations, but are also etched in geometries we are only just learning to see. If we can render the mirror, what other hidden structures of reality await their moment in the light? Visualizing the mirror does more than enlighten, it transforms how we understand knowledge itself. This profound synthesis is already reshaping the very architecture of advanced education, pushing mathematics beyond its traditional silos. For generations, students learned geometry, algebra, and topology as separate kingdoms, each with its own language and rules. Homological mirror symphony demands they be seen as one interconnected realm. It forces a fusion, showing that the dynamics of a symplectic space and the equations of a complex variety are two perspectives on a single truth. This is not just a graduate-level novelty, it is a blueprint for a more holistic intellectual lifestyle. Curricula at the cutting edge are beginning to reflect this, introducing category theory not as an esoteric finale, but as a foundational language much earlier. The goal is to cultivate a categorical way of thinking, where the primary focus shifts from calculating isolated objects to mapping the networks of relationships between them. Imagine a future classroom where an aspiring engineer first encounters the concept of a vector space not through rows of numbers, but as an object in a category, defined by how it connects to other structures through linear maps. This frames the entire subject as a study of possible transformations, which is precisely what engineering is. A programmer might learn data structures through the lens of functors, understanding that a good software architecture is one that preserves essential relationships when translating data between different modules. This is systems thinking made concrete. The mirror teaches that a problem intractable in one framework might become simple when viewed from its dual perspective. That lesson in flexible problem solving is priceless. It trains minds to seek not just the answer, but the most insightful language in which to phrase the question. This educational shift fosters a new kind of intellectual agility. Students learn to hold two seemingly contradictory descriptions in mind simultaneously, recognizing that both can be true and that the power lies in the translation between them. They stop asking, "Is this geometry or algebra?" and start asking, "What is the categorical bridge that links them?" This mindset is the ultimate tool for navigating a complex world. It prepares future innovators not to memorize fixed facts, but to navigate the fluid landscapes of modern science and technology, where breakthroughs happen at the intersections. The legacy of the mirror, therefore, may be its quiet revolution in how we learn. By placing duality and relationship at the heart of understanding, it cultivates thinkers who see the hidden connections in everything, from the code they write to the physical systems they design. The mirror does not just reflect mathematics, it reflects a better way to build a thinking mind. The profound elegance of a mathematical proof can stir the soul in the same way a symphony does. Homological mirror symmetry, in its perfect balance of motion and form, is not merely a tool for calculation, it is an object of breathtaking beauty. Its central idea that two utterly different descriptions can capture the same essential truth resonates far beyond the chalkboard, touching the very heart of artistic creation. This is the aesthetic of duality, a principle that has inspired artists for centuries, from the mirrored compositions of Renaissance paintings to the call and response structure of a blues song. Now, with modern technology, we can render this abstract beauty into forms we can see and feel, making the invisible architecture of the cosmos a source of public wonder. Generative artists are the new explorers of this landscape. Using algorithms derived from the very equations that define Calabi-Yau manifolds, they create stunning digital sculptures and animations. These are not literal illustrations, but emotional interpretations. An artist might feed the parameters of a mirror pair into a custom program, allowing the software to generate a flowing, organic form that represents the Fukaya category's dynamism, and a corresponding crystalline geometric structure that represents the derived category's rigidity. The resulting diptych is a visual conversation, a silent film about equivalence. You can find online galleries where hypnotic loops show a shape that seems to breathe and flow seamlessly, transforming into its static, intricate mirror twin, a direct visual metaphor for the functor translating one world into the other. Other pieces visualize category diagrams themselves, transforming networks of objects and morphisms into pulsating constellations of light, where connections glow with the intensity of their mathematical importance. To witness these pieces is to understand intuitively that mathematics at this level is not about cold numbers but about profound and beautiful pattern. Conceptually speaking, a digital artist working with these algorithms becomes a collaborator with the mathematics. They set the initial conditions, the seed of a symplectic form or a complex structure, and then let the logical rules of the mirror correspondence play out, often with surprising and sublime results. The artist curates the output, choosing color palettes that highlight contrast or harmony, and framing the result in a way that invites emotional engagement. In interviews, such artists often speak of feeling like they are uncovering a pre-existing beauty, not inventing it. They describe their work as a form of translation, not between languages, but between the abstract realm of pure relation and the sensory realm of human perception. Their art asks a powerful question: if the universe's deepest laws are mathematically beautiful, should not our appreciation of that beauty be considered a core human experience? This leads to a compelling argument for the place of such abstract appreciation in a modern, fulfilling life. We readily accept that immersing oneself in great music, standing before a monumental painting, or walking through a masterpiece of architecture enriches the human spirit. These activities cultivate wonder, refine our taste for complexity and resolution, and connect us to the pinnacle of human creativity. Engaging with the profound elegance of homological mirror symmetry offers a parallel form of enrichment. It is an intellectual aesthetic, following the logic of the mirror map, appreciating the shock of a duality that makes the impossible calculable, delivers a unique form of joy, the joy of insight. It expands our sense of what is possible and reveals a hidden harmony in the fabric of reality itself. In a world often dominated by utility, taking time to marvel at such a purely beautiful idea is a radical act of cultural sophistication. It asserts that understanding, even at the most rarefied levels, is not just for specialists, but is a legitimate and thrilling part of a life well lived. The mirror, therefore, reflects not just geometries, but a path to a deeper kind of wonder. Sameness is a far stranger concept than it first appears. We think two things are the same if they are identical, if every single point matches up. But homological mirror symmetry shatters that naive view. It shows us that two geometric worlds can be profoundly, perfectly the same in their deepest structure, while being built from entirely different materials and governed by completely different rules. They are categorically equivalent, meaning their entire network of possible relationships is identical, yet they are not point for point the same object. This is a philosophical earthquake. It forces us to ask, what does it truly mean for two things to be the same? Is it about their substance, their raw ingredients, or is it about their form, their pattern of connections? The mirror answers resoundingly for the latter. Reality, it suggests, is relational at its core. An object is defined not by what it is made of, but by how it interacts with everything else in its universe. This idea has deep roots. The philosopher Gottfried Wilhelm Leibniz proposed something called the identity of indiscernibles. It states that if two objects have exactly the same properties, then they are, in fact, one and the same object. There can be no two distinct things that are perfectly identical in every way. Homological mirror symmetry presents a stunning mathematical counterpoint. Here we have two distinct spaces, a symplectic manifold and a complex variety. They do not share the same points, the same coordinates, or the same local properties. A point in one has no direct counterpart in the other, yet at the categorical level they are indiscernible. Every possible relationship in one finds a perfect mirror in the other. Their relational properties are identical, so are they the same or not? The mirror forces a more sophisticated answer. They are the same in essence, in information, but not in presentation. This has startling echoes in modern thought. Consider the simmering debate about simulated realities. If we one day created a perfect simulation of a universe, a digital cosmos where every interaction, every law of physics was perfectly modeled, would that simulated universe be real? A substance-based view says no, it is just silicon and electricity. But a relational, categorical view inspired by the mirror might say yes. If the network of causal relationships, the structure of experience and interaction within the simulation, is perfectly equivalent to our own, then in the only way that fundamentally matters, it is real. Its substance is different, but its soul, its categorical blueprint, is the same. This perspective also illuminates twin theories in physics, like the gauge-gravity duality we touched on earlier. Physicists are not saying a black hole in a warped spacetime is literally, point for point, the same as a hot soup of particles on a boundary. They are saying the theories are equivalent, their relational structures map onto one another perfectly. The physics is the same story told in two alien languages. This is the profound gift of the mirror mindset. It trains us to look past the surface presentation and seek the underlying structural isomorphism. In our own complex, interconnected world, this is a vital skill. We constantly encounter systems that appear different on the surface, a biological ecosystem and a digital social network, a city's traffic flow and the firing of neurons. A relational view asks not what they are made of, but how their parts connect and communicate. It looks for the hidden categorical equivalence, the shared pattern of relationships that might allow insights from one domain to solve problems in another. The mirror teaches that true understanding often lies not in dissecting the substance, but in mapping the connections. It suggests that identity itself is not a property of an isolated thing, but an emergent feature of its place in a web. So the next time you ponder what makes something what it is, remember the mirrored manifolds, whispering that sameness is not about matching points, but about mirrored patterns. A conjecture is a brilliant guess, but a theorem is a fact of the universe. The journey from one to the other for homological mirror symmetry is not a single, decisive battle, but a sprawling, collaborative campaign of verification. This is the meticulous work of turning a stunning vision into a reliable map, one landmark at a time. Think of it as explorers charting a vast, mysterious continent. The original conjecture gave them the belief that the continent existed, but proving it meant landing on specific shores, climbing particular mountains, and drawing each valley with precision. There is no single proof that covers every possible landscape. Instead, mathematicians build a growing web of verified examples, each one adding another solid piece to the territory we know is truly mirrored. The tools for this mapping expedition come from the deepest arsenals of modern mathematics. Homological algebra provides the precise language for comparing categories, the ruler and compass for measuring equivalence. Deformation theory allows mathematicians to gently bend a space, studying how its mirror partner responds to these nudges, ensuring the duality holds not just for a single, rigid shape, but for whole families of related geometries. From the symplectic side, symplectic field theory offers powerful techniques for analyzing the behavior of pseudo-holomorphic curves, those ghostly sheets that define the morphisms in the Fukaya category. And increasingly, computer-assisted proof plays a crucial role, using algorithmic algebra systems to verify the thousands of intricate calculations required to check that a proposed mirror functor works perfectly for a vast list of objects and relationships. Each successful verification for a new class of spaces is a major victory. The early triumph for elliptic curves, the donuts, was the first secure beachhead. Then came the mapping of projective spaces and, significantly, toric varieties. These are spaces built from simple geometric blocks like high-dimensional polygons, and proving mirror symmetry for them provided a huge, fertile province on the map. More recently, the frontiers have expanded to include cluster varieties, spaces whose geometry is governed by combinatorial patterns that constantly mutate and rearrange. Proving mirror symmetry here feels like discovering that even the most dynamic, shifting landscapes have perfect, static reflections. This ongoing verification game is far from dry paperwork. It is a testament to the conjecture's shocking robustness. Every time mathematicians stretch the duality to a new, more complex class of spaces, and the mirror holds, it is as if the explorer's map predicted a river exactly where they found one. The continent is real and its laws are consistent. This process of proof by example is a major, vibrant activity in the field, a collective exercise in confidence building. With each new piece of the map filled in, the mirror changes from a dazzling hypothesis to an established feature of the mathematical world, a dependable bridge we can use to travel between realms. What uncharted territories on this map are the explorers eyeing next, and what tools will they need to claim them? The machinery behind the mirror is both intricate and profoundly elegant. To truly appreciate the translation, we need to open the toolbox and examine a few of its most essential instruments, not as abstract symbols, but as powerful ways of organizing geometric information. Let us start with sheaf theory. In its simplest form, a sheaf is a radical upgrade to the idea of a function. An ordinary function assigns a single number to each point on a shape. A sheaf assigns an entire structured set of data, like a vector space or a module of algebraic functions, to every open region of a space. Crucially, it comes with a rulebook for how the data on overlapping regions must agree, how they glue together seamlessly. This turns a geometric shape from a set of points into a layered, local-to-global information system. A coherent sheaf is a particularly well-behaved version, acting like a generalized function that can capture not just values, but also directions, twists, and singularities. The derived category of coherent sheaves is the grand library built from these objects, where the focus shifts to entire complexes or chains of sheaves. This library does not just catalog static objects, it encodes the possible algebraic transformations between them, the entire relational algebra of the complex geometric world. It is the rigid, crystalline language of the B model, On the opposite side of the mirror, the dynamic world speaks through the Fukaya category. Here, the fundamental objects are Lagrangian submanifolds, those special membranes in the symplectic sea. But defining their category rigorously is an analytical odyssey. The core challenge is defining the morphisms, the relationships between two Lagrangians which are meant to be their intersection points. The first hurdle is transversality, ensuring the Lagrangians intersect cleanly in discrete points, not in messy, infinite families. This can often be arranged by gently perturbing the objects. The far deeper and more beautiful challenge is bubbling. Imagine you are counting the ghostly soap films, the pseudo-holomorphic disks that connect two intersection points. Sometimes, as you vary parameters, a disk can degenerate, developing a bubble, a smaller disk that pinches off. This bubbling phenomenon means the simple count of disks is not stable, it can suddenly change. The monumental achievement of Floer and Fukaya was to develop a coherent theory that incorporates these bubbles, using a technique called virtual cycles, to produce a count that is invariant and defines a true category. This makes the Fukaya category a soft, quantum counting machine, inherently tied to the analysis of possibilities. For geometries that are not closed and compact like an infinite plane, the story expands further with the wrapped Fukaya category. Here, Lagrangians are allowed to extend out to infinity, and we consider not just their intersections, but also the ways they can be wrapped around by the symplectic flow at the boundary. This introduces a whole new class of morphisms, capturing dynamics that escape to the frontier. These tools, from the algebraic glue of sheaves to the quantum analysis of Floer trajectories, are the gears and pulleys of the mirror functor. They transform the beautiful conjecture into a working apparatus, one that can actually compute, translating a question about algebraic bundles into a problem of counting trajectories in a space of flows. This is the deep machinery that makes the reflection not just a metaphor, but a precise, calculable fact of the mathematical universe. 50 years from now, the mirror's quiet logic may have rewritten the rules of invention. Picture a quantum architect's studio, not with drafting tables, but with a console that manipulates symplectic geometry directly. An engineer needs a new battery membrane, one that must guide ions with perfect efficiency. Instead of simulating endless chemical combinations, she describes the desired dynamic property, the ideal flow of energy, as a symplectic condition. She feeds this abstract description into a quantum algorithm born from the principles of homological mirror symmetry. The algorithm, functioning as a synthetic mirror functor, does not compute a single answer. It explores the categorical landscape of all possible solutions. In moments, it returns not a chemical formula, but the algebraic blueprint of the membrane's mirror partner, a complex shape whose rigidity and stability directly encode the desired ion dynamics. A fabrication unit then materializes this algebraic shape at the nanoscale, knowing that its geometric twin, the one with the perfect flow, is guaranteed to exist in the physical material. The mirror has become a design oracle, turning a description of a desired function into a blueprint for a form. In this future, the most valuable software for an aerospace engineer or a synthetic biologist might be a category compiler. Faced with a chaotic problem of fluid turbulence over a new wing design, a problem drowning in non-linear dynamic data, the engineer simply feeds the symplectic data stream into the compiler. The software, trained on vast libraries of proven mirror pairs, instantly constructs the mirror algebraic problem. Suddenly, the turbulence is represented not by unpredictable vortices, but by a system of polynomial equations describing stress distributions. The engineer solves for stability in this algebraic realm, and the compiler translates the solution back into a physical adjustment to the wing's surface. The boundary between the dynamic world of forces and the static world of equations dissolves into a seamless workflow. This is not mere simulation, it is categorical translation, using the universe's own dual perspectives as a problem-solving engine. Even our digital security could be reforged in the mirror's image. Today's cryptography often relies on the computational difficulty of problems like factoring large numbers. Future cryptosystems might be built on categorical duality itself. Imagine a cryptographic protocol where the public key is the Fukaya category of a fantastically complex symplectic space, a vast dynamic web of Lagrangian relationships. The private key is the explicit mirror functor that maps this tangled web to its derived category on the algebraic side. To encrypt a message, you encode it as a sequence of operations within the public symplectic category, a path through its maze of possibilities. Without the functor, the mirror map, decrypting this is an impossible task, akin to deducing the plot of a novel from a single, garbled page in an alien language of motion. Only with the secret functor can you translate the dynamic path into its algebraic counterpart, where the message resolves into clear, logical steps. The security lies in the profound difficulty of reconstructing the mirror functor from the category alone, a problem that sits at the heart of HMS itself. The most sensitive secrets would be guarded by the complexity of geometric duality. In this speculative century, the greatest shift is cultural. The conceptual engine of HMS, the habit of seeking dual descriptions, becomes as fundamental to innovation as calculus once was. Laboratories for fundamental physics and studios for industrial design speak the same categorical language. A physicist probing quantum gravity with a gauge duality, and a musician generating harmonic structures with an AI trained on derived categories are, in a deep sense, using the same mental tool. The mirror teaches that the deepest truths are relational, and that every problem has a hidden twin where the solution might be elegantly simple. This future is not about everyone understanding the chain rule of a mirror functor, but about a society that instinctively looks for the reflection in the chaos, knowing that the most powerful answer often lies on the other side of a looking glass we have only just learned to see. We have traced a line from the swirling dynamics of a pendulum's phase space to the frozen lattice of a Calabi-Yau manifold, all connected by the silent translator of category theory. This is the epic journey of homological mirror symmetry, a bridge built from a physicist's intuition in string theory and forged into a mathematician's precision tool. It began as a whisper between worlds, a conjecture that the language of motion and the language of equation were telling the same story. That whisper grew into a roar of computational power, turning impossible counts of hidden curves into solvable differential equations and offering a blueprint where quantum stability might be etched in geometric shape. It has become an inspiration for machines that could think in dualities and a new lens for seeing beauty in the deepest structures of thought. This journey reveals a universe that speaks in reflections, where the most profound truths are not singular statements, but harmonies between perspectives. The next great leap for this mirror may not come from a mathematics department at all. It could emerge from a materials lab seeking unbreakable polymers, a cryptography team designing unhackable codes, or an artist's algorithm generating unseen forms. Its potential is unlocked by a simple, relentless curiosity about connection. So we ask you, as this exploration closes, which reflection captivated you most? Was it the link to the cosmic strings of theoretical physics, the promise of a revolutionary computational engine, or the philosophical shift that redefines sameness itself? Share your thought in the comments below and keep looking for the mirrors hidden in the fabric.